The following message is best viewed on an oscilloscope.
Okay, do we have our first speaker here? I'm sorry, I just got here.
Hi, I'm here.
Okay, great.
Should I start sharing my slides?
Yes, please go ahead. Yes.
So, do you want me to start?
Yes, we'll hear about fast simulation at LHCb.
Okay, indeed. So,
Adam, just to say your slides have got a participants mini window in front of them.
right, okay.
Yes.
That. Hopefully that's better. There's a strange outline on mine in my top left corner. I don't know if that's the same for everyone
I see
else.
that too. I don't know what it's from.
What if I make... I will stop the share and start it again. It should be... Okay, I think that's a bit better.
Yes, it is.
Right.
Thank you.
Okay, so I'd like to first thank the organizers for giving me the opportunity to speak. I'll be presenting the array of fast simulation options available at LHCb. So just an introduction to the experiment. So on the left, we have a diagram where the different subdetectors are kind of grouped together and labeled. There's a link to the 2008 JINS paper describing the experiment. And if you want to know more about the upgraded version, which is currently being installed, there's a talk given by Federico yesterday, which is quite enlightening. So for the context of fast simulation, already we've seen in run 1 and run 2 that some analyses, particularly things like semi-leptonic analyses, which need large Monte Carlo samples for things like template fits, to simulate these samples with full detailed simulation would be prohibitively expensive in terms of computing resources. And also in the in run 3 and onwards, we have an increase in the luminosity, which means that there are more numerous and complex events. Therefore, fast simulation options which produce more events with less resources are absolutely necessary. To really drive home this fact, we have this plot of the projected computing resources over the next few years, where you have the pledge is this solid red line. So this is the available resources. The bars are the prediction of the computing resources using 100% detailed simulation for every sample. And we have this solid blue line is if we have we introduce widespread use of fast simulation techniques, and we have another line with our so-called aggressive fast simulation model. So for an overview of simulation at LHCb, you'll often see diagrams of this form. So we can talk about applications that we run. So we have one called Gauss and one called Boole. So Gauss does the particle simulation and Boole does the digitization. And then the samples are passed off to Moore and Brunel, which run the trigger and reconstruction, which also run on data. Brunel will be removed for run 3, and there is a talk about this by Renato there. So within Gauss, you can divide this into 3 steps. The first is generation. So we do the proton-proton collisions or lead-lead collisions, what have you. Then there is the decay step, which is usually done by EVT gen. And then we have propagation, which is at the moment exclusively done by jump 4, I believe. And this is actually the step which takes up 95 to 99% of the whole CPU time for this entire chain, from generation to reconstruction. So, you know, let's think about what are the things that we can do to speed this up. So the obvious things with any kind of slow computation problem, you can optimize the code or introduce multi-threading. But also specific to particle simulation, you can do things like simulate fewer particles. So we have 3 techniques for doing this. And the idea of this is to give fewer particles to jump 4, so it takes less time. You can also simulate less of the detector. So particularly the rich and the calorimeter, which I'll cover later, are very slow to simulate. So you can just switch these off. And you can use faster techniques than jump 4 for sub-detector simulation, perhaps at the cost of some detail. So LHCb has a growing menu of fast simulation options, which are listed on the left. I won't cover the fast calo because there's a dedicated talk immediately following mine. So the first 3 kind of cover the generation phase, and the idea, like I said, is to give fewer particles to jump 4, and the rest are covering the simulation of the detector. So let's cover these in the order I just presented them. So the first thing you can do is what we call particle gun, which is where you just generate the signal particles without the rest of the event, and then you can apply some vertex smearing in the reconstruction to make it more lifelike, let's say. This is very quick, it's roughly 50 to 100 times faster, and has an additional advantage of using 1/100th of the disk space. It's useful for quick checks, but has limited suitability for physics analysis. And one good example is centrally exclusive production-like analysis. The obvious disadvantages are there are no information of the underlying event. You can have variables even related to the signal which are affected by the local occupancy within the detector, which will be poorly reproduced. And one of these is, for example, the track chi-squared per degree of freedom, which is shown on the right, where you see some disagreement between particle gun simulation and nominal simulation. Kind of a more advanced version of this is redecay, where you do have an underlying event, but you use it many times for many signal decays. So the idea is that you generate one full event, you delete your signal decay, which I've shown here as a red, bunch of red lines. And you can generate several further signal decay and merge them with the same underlying event. So this is configurable to generate as many as you like. We typically do productions with 100 decays, and you can also choose which particles to redecay. So I showed an example in the diagram of the signal-only version. You can also choose like the heaviest answers, or all heavy flavor particles and things like this. So the advantage of this, the advantages, plural, rather, are that this is independent of the choice of generator. So you can run with Pythia, Gen, SciC, BC, VegPy, things like this. And it can be combined with other fast simulation options. So you can also speed up the detector simulation itself. So this has a speed up factor of 10 to 50 times, depending on the type of event. One thing to be cautious about is that there is generally a loss of statistical independence between events, which means that the statistical uncertainties are generally greater than Poisson uncertainties, depending on the type of variable. Here on the right, we have a plot of a variable which is not really affected by this. This is some invariant mass distribution of a signal candidate, which is generated, independently in every event. So what's plotted here are just the Poisson uncertainties, and you can see that from the pool distribution that it agrees quite nicely. But if you were looking at something like the eta of the signal, this would have much larger uncertainties. And this is good for LHCb because this is the type of analysis that we generally study. We're concerned with these types of variables. And this can be treated properly by using block bootstrapping, where you just sample events with the same underlying event. One disadvantage of this is it's only suitable for generating samples where you have a specific decay that you want to repeat. So not, for example, minimum bias samples. And we can see that this is introduced maybe early 2019 and has been adopted quite enthusiastically within the collaboration. So you can see in a 12-month period that redecay accounts for a majority of the events simulated. Another technique which is on similar lines is something called split sim, which is where you simulate part of the event before deciding whether to simulate the rest of it, which kind of relies on the same kind of splitting and merging techniques as redecay. So this gives you more efficient filtering on material interactions or particles decayed by jump 4. So an example of material interactions is, of course, converted photons, or K-short decays are actually done by jump 4. So moving on to the techniques that target specifically the detector simulation, here's a plot of the percentage of the time spent simulating each subdetector. And you can see that the rich 1 and rich 2 are taking up a lot of time, as well as the calorimeter, particularly the ecal. And on the right here, you can see these kind of grouped together. So the calor and the rich are taking up most of the time. So the kind of obvious thing to do is switch off the rich. So this means disabling the generation of optical photons, Cherenkov photons, but still simulating the kind of material interaction with the rich detector. So there's no impact on the downstream detectors. This gives you a roughly 30% speed up and a slight reduction in the disk usage, but at the cost of no simulated hadron PID. But this can be worked around by using existing parametric techniques that we kind of use anyway. So an example of this is PID calib, and there's a link to a public note about that. And the disadvantage of this is it requires special trigger and offline selections. And this has been validated on, I believe this is a muonic RD style analysis, where to get this peak, I believe some PID is important. A kind of more extreme version is to do tracker-only simulation. So if you cast your minds back to the very first slide, the calorimeter and muon and the rich all come after the tracking system, apart from rich 1. So you can remove these entirely and not simulate the calo or muon or rich 2. This gives you a roughly 10 times speed up and uses a quarter of the disk space, but you have no particle innovation at all. And the hardware level trigger is not simulated, and you kind of, it's up to you to do this yourself. But we can see that for a similar plot with a similar analysis, it gives very good. It compares very well with the detailed simulation. So moving on to the last technique I will present. So doing fully parameterized detector simulation. So in some sense, skipping the Jean 4 equivalent entirely and going straight to reconstruction level objects. So there is an existing tool called Delphis. There's a link here to the paper. So when we looked at this, we saw that LHCb geometry is not natively supported. We use a Cartesian geometry rather than a kind of cylindrical one. So we implemented a dipole magnet and a Cartesian calorimeter segmentation. And then it was found that the interfacing with our Gauss, our simulation application, required some extra steps. And in the code review, there were duplications and complications, which led to the eventual decision to proceed with an in-house detector parameterization called Lamar. But this work did not go to waste. The LHCb implementation of these things will be pushed upstream to Delphis for use in the wider HEP community. So just one slide on how Delphis works. The idea is that you propagate the MC particles to all points of interest, i.e. the subdetectors, and then smear and apply efficiencies. the track info is sampled with from using a inverse cumulative method. The calorimeter parameterization is inspired by Delphi's and uses simple loops on the geometries. PID information is computed using stacked generative adversarial networks. And the output of all this is high-level objects used in physics analysis. So the validation of Lamar was done using 2016 data and kind of out of the box with not much tuning. So on the left we have a example lambda C mass peak where we're comparing the purple points with the solid blue line here. You can see there's some disagreement and some refinement is necessary. A distribution which is reproduced quite well is on the right. So you have proton momentum where you see Lamar output in purple and some data in light blue. And the performance of Lamar is quite impressive. So these are plots from Valgrind and Cashgrind generating 50 events with both Delphis and Lamar. The propagation and high-level particle making is this kind of brown sliver on the right of the Lamar plot. And these plots are scaled so that the particle gun which generates the particles gives the same area. So Lamar overall runs much faster. And future improvements will focus on TensorFlow memory management and multi-threaded generators for the calorimeter clusters. So to summarize, fast simulation is absolutely necessary to meet the current and future demands of LHCb, and there is a growing suite of techniques and developments that are ongoing. These are complementary options that can be combined, and we've already seen successful adoption of several techniques already. There are several more on the horizon. And I'd like to advertise Matteo's talk, which immediately follows mine. So, thank you.
Okay. Do we have any questions? Does anybody want to raise their hand? Okay. Oh, here we have one from James Catmore.
Oh, hi, can you hear me okay?
Yes.
So thank you for the very nice talk. I just wanted to ask whether with so many different flavors of fast simulation, is this a problem that you have to have different calibrations for each one and that these take a lot of time to prepare and need a lot of person power, etc.? Do you find that having all these different flavors causes problems in integrating this with the final analyses?
So the way that LHCb analysis are done anyway, there is a lot of per analysis calibration. Like I mentioned, this PID calib tool, which we kind of have to run to get nicer PID variables. So in some sense, it's not that different to business as usual. Yes, indeed, there are, so like with the Trackeroni, for example, with the muonic RD star analysis, they had to kind of come up with their own recipe for the hardware level trigger for getting that information out. So yeah, there is a bit of an overhead for introduced by these different techniques.
Okay, thank you.
Okay. I have one question, and I was impressed by your collaboration's uptake of the fast simulation technique. I mean, how do you get the word out to them that computing resources are scarce and they should consider a fast simulation?
Well, before I got involved with LHCb simulation, the way the word propagated to me was through the Tuesday meetings and the the internal collaboration meetings. So I think everyone is quite familiar with the plot of how this one where the the demands will outstrip our resources in the next few years.
So they see it as an investment then, in a sense, because it does take them extra work, right, to
yes,
adopt it. Right. Okay, that's interesting. Okay.
And also there was a kind of a top-down approach from like the working group conveners who have to approve every request will you know, ask, can this be done with fast simulation?
Ah, interesting. Okay. Well, thank you. I think I don't see any more questions here.
Okay.
So next we have talk about the fast calorimeter simulation in LHCb by Matteo. Are you?
Yes, can you hear? Can you see me actually?
Yes, I can see you.
Okay.
Great. And can you share your screen?
Yes, just a moment. Right, should be shared now. Let me. This one, this.
Yes.
All right. So tell me when I can start.
Go ahead.
Okay, so I will present the ongoing effort to develop a fast simulation of the LHCb calorimeter at the heat level. Okay, so the application, sorry, okay. So the application for the simulation of the particles in the LHCb detector is called Gauss, and it takes care of it takes care of both the particle generation and the particle transportation in the detector. The latter part is made using the Gen 4 toolkit, which is quite accurate, but as you probably know, it's also quite CPU time demanding. And for this reason, the number of simulated physics events in the experiment are limited by the computing resources. So obviously, from this follows our need of fast simulation. So the fast simulation techniques that are currently in production or almost in production, as Adam has explained, are all based on a partial simulation of the event or a partial simulation of the detector, or using a fully parametric approach. Here, I'm going to describe the ongoing efforts to develop a faster detector simulation at the heat level, aiming at the same quality as the full C simulation based on Gen 4. So in this plot here, you can see how the CPU time per event is spent as a function of the different subsystems. You can see that the calorimeter and the reach detectors dominate, take about 85% together, and the calorimeter takes about 35%, so it is a good place to start developing a faster detector simulation at the heat level. So on the left here, you can see a scheme of the LHCb detector with the red arrow indicating where the calorimeter system is placed. The calorimeter is composed of 4 subsystems: a scintillator pad detector, a pressure shower, and the 2 main systems, the electromagnetic calorimeter and the hadronic calorimeter. Here in the one thing to notice is that these subsystems from the readout point of view are not longitudinally segmented, so that our heats are, let's say, covers a 2-dimensional plane as opposed to a 3-dimensional space. Okay, this is important for the parameterization of the clusters later. Here on the top, on the bottom plot on the right, you can see a quarter of the ICHEP schematic view. In black, the beam pipe hole, and then in red, blue, and yellow, the inner, middle, and outer sections with different cell sizes, ranging from 4 centimeters up to 12 centimeters. Okay, so we are developing an interface which makes possible for each simulated particle which reaches the calorimeter to choose whether the particle should be simulated in a fast or full mode inside the calorimeter, and this depending on the particle type, on the kinematics, and on the entrance position of the particle. In this example depicted here, for instance, the muons reaching the calorimeter, which is represented by the red box, are still propagated by Gen 4, while the photon G4 shocks are killed at the entrance of the G4 region, and then are fast generated. Okay, this interface also allows, if needed, to use different models in the same event, depending, for instance, on the particle type or on the particle energy. Okay, so it is quite flexible. So concerning the development of the actual fast simulation of the calor response, there are two independent lines of development. One which uses machine learning techniques, and the other one which uses a library of energy deposits. However, the common goal, of course, is to fast generate the calor hits as a function of the XMP of the particle and as a function of the particle type. The final choice will be based on several considerations, including the output quality, the readiness. But let's keep in mind that from the time gain point of view, both we already know that both approaches give gain well above a factor of 10 at levels where the impact on the overall event time is negligible. And then let's also remember that in principle, it will be also possible to use both techniques at the same time if these will prove to be useful. Okay. Okay, so let's start from the development line concerning the use of machine learning technique to simulate the calorimeter response. There is an ongoing effort to investigate the use of generative adversarial networks to generate the hits. Some preliminary results have been already presented in other occasions. Here, for example, there is a link to the Chapter 18 proceeding. Here, the Gen4 is used to simulate the cal modules and to generate the real hit distributions, which are then used to train the generative adversarial networks, so the GAN. And here you can see an example of comparison between Gen4 and the GAN output. In general, we see good agreement between Gen4 and the GAN for primary cluster characteristics. Here on the right, you can see, for instance, the distribution of the transverse width of the cluster, while there is a bit poorer agreement for secondary cluster characteristics. In the meanwhile, the team of developers has changed, and the different architectural approach is currently being investigated. So the idea here is to combine two generative models, the variational autoencoder and the GAN. The training of the variational autoencoder takes as input the real hit distribution, which is then encoded by the encoder into a lower dimension vector, which is then decoded by the decoder into a new image, which is compared with the original one. And through a loss function and a backpropagation feedback, the variational autoencoder learns how to generate hit distribution starting from an input encoded vector. Okay, while the generative adversarial networks are basically composed of two competing networks: a generator whose goal is to generate hit distribution as close as possible, as similar as possible to the real one, to fool the discriminator, and the discriminator aims at distinguish between real and fake hit distributions. Ideally, when the training is complete, the discriminator will not be able to discriminate between real and fake hit distributions. So one attempt that is being investigated is to combine, as I said, the variational autoencoder with the GAN, where in practice the variational autoencoder is trained, and then the pre-trained decoder takes as input a noise vector and produces as output a distribution of hits, which are then passed to the generator of the GAN. And with this technique, the hope is to make the training of the GAN a little bit more more stable and more manageable. So here you can see some preliminary comparisons between Gen 4 and the machine learning networks that I've just mentioned. So you can see on the top left an example of real heat distributions. Real means here Gen 4. And then an example of the distribution as output from the variational autoencoder and the result from the combination of the variational autoencoder with the GAN. So the autoencoder trains well, but the results are often a little bit blurry, as you can see. When it is combined with the GAN, the results is slightly better. However, it is not, let's say, I mean, the level of accuracy reached so far, it is not yet enough, and more work is still needed to further refine the current model or try different models. Here on the right, I will put a link where you can find the name of people working on, of the team working on this part, and also some more details on the ongoing work. Okay, so now let's say I want to tell you about the other development line where basically we full simulate single particles at the SPD entrance, so at the Calo system entrance, for a discrete set of energy angle of incidence and azimuthal angle of the particle. And we take the generated calorimeter hits and we store them in a root file, which is basically the library. Okay. Right now we are testing a configuration where we have just one node in the azimuthal angle and 80 different values for the energy ranging between 1 MeV and 100 GeV, and 14 nodes for the angle of incidence. Then when the fast simulation is switched on and the particle reaches the calorimeter, the heat simulation that would have been generated by Gen 4 is replaced by a heat collection which is taken randomly from the library. Note that in our case, the library is not actually a collection of cell heats, but rather a collection of energy deposits in much smaller regions that we could call points or pseudo points. So we can talk about the point library. So to have an idea, consider the figure on the right of the slide. This is the overall square is a representation of the inner cell with a side of 40 millimeters, and this is split into 25 subcells, and each of these subpoints, subregions, is a point. So contains the energy deposited in that subregion. And the idea of using, let's say, points is crucial because it allows to have a much better performance of the library for a given library size. Okay. So then once we have picked a hit point selection collection from the library before being used, these points are transformed to match the characteristics of the incident particle. So if you consider on the left plot, the original energy deposit collection which has been taken by the library, then it is slightly changed to take into account that the particle doesn't fall in general exactly into a library node, but it will be close to one of the nodes. So it will require a slightly modification. Then the points are rotated in the azimuthal, from the point of view of the azimuthal angle to match the azimuthal angle of the entering particle. And this is described by the third plot from the left. And finally, the points are translated to match the entrance point of the incident particle. Okay. All these corrections takes a negligible amount of time, so they don't have basically an impact on the time associated to the use of the library. So here is an example. So an example of our current format for the library. The information, so the hits are stored in terms of vectors or vector of vectors. Just to give you an idea, for a library with 80 nodes in energy, 14 nodes in the azimuthal angle, and 100 collection for each node, we have a size of about 115 megabytes for photons. Okay, so now let's see the comparison between the fast simulation of the calorimeter using the library and the Gen 4 simulation, so the standard simulation that we use in LHCb. We have built a library with the, as I said it again, with the particles with an azimuthal angle of 90 degrees and with the particles entering in the calor intersection. And we apply this library for particles entering the calorimeter from the middle section, so in a completely different region, and with azimuthal angle of 45 degrees. So the transformation that I mentioned before need to be applied to use the heat collection taken from the library. And here you can see the comparison of some parameters of the cluster. On the left and in the middle plot, the cluster width in the horizontal and vertical direction. Black is Gen 4 and red is the library. While in the rightmost plot, you can see the distribution of the ratio between the cluster, total cluster energy, and the energy of the incident particle. And you can see that the agreement is reasonable, is not bad. While here, the comparison is done directly into a simulated and reconstructed decay channel in B0 to K star 0 gamma, where the photon is reconstructed in one case with a standard selection, in the other case using the library. And so first of all, it's important to stress that the reconstruction efficiency are very similar, consistent with the 1% relative uncertainty in both cases. There are some residual differences, as you can see, in the shape of the mass. So some additional tuning needs to be done, but we already, have some ideas on where to try to improve the agreement. Okay. And that's it. So to summarize, there is an ongoing development of the interface that will manage the fast and full simulation of the detector, of the calorimeter in particular, at the heat level in the LHCb simulation framework. This will allow to switch off or on the fast simulation as a function of the particle property. And we are investigating two lines of development, one based on machine learning, one based on the library. In both cases, the results look promising, but there is still more work to do to improve the accuracy and the quality of the comparison with the Gen 4 simulation. This is all work in progress.
Oh, thank you. Do we have any questions for Matteo? No, I don't see any.
Well, Liz, I have a question, but because I'm a co-host, I can't put my hand up.
Oh, go ahead then.
Features of Zoom. Yeah. So Matteo, that was a really nice talk. Thanks for running over all of those different techniques. I was wondering, just sort of comparing it to Atlas and the fast simulation that we do there. One of the things that we find is that there's a lot of information stored effectively in where the primary particle hits inside the calorimeter cell. So for instance, the showers that we would get from a center hit look quite different to the ones that we would get if we get an edge hit, where then the energy gets spread quite evenly between the two cells which are close. And I was wondering if you have this issue inside of LHCb and if you need to take it into account, because we found at the hit level, we actually need to condition on the hit position inside the cell as an additional variable.
Yeah, okay, no, it's a good question. So we do see some differences, but not so large, okay? So the example that I've shown here in these comparisons, no, this one. So basically, the library was created from photons generated exactly at the same position in the same cell. So it doesn't take into account possible variation of the response within the same cell. And this could be actually one of the reasons of this not perfect agreement between the red histogram and the black histogram. What we would like to do, so yes, there is a difference, but no, it's not extremely large. What we would like to first attempt is to build a library where the particles are not generated all exactly in the same point in the cell, but with some, let's say, uniform distribution to see whether from the statistical point of view, this can improve things. One other thing that I should mention is that this was one point. The other thing is that after the hits are taken from the library, they are given to the same code that is given when the Gen 4 is used, which among the various things also apply some corrections based on where the energy deposits is within the cell area. Okay, so some correction is already taken into account in any way. But as you can see from this comparison, this is not enough. One other possibility that we have in mind to use maybe on top of the one that I've mentioned is to apply some, let's say, corrections or some calibration on top to correct for this dependence on the position within the cell. All things that we have to still fully investigate. But yes, it's a good point. It's something that we have to face too.
Yeah, thanks.
Yeah, thank you, Matteo. I think we are pretty much on time. If we have our next speaker, Mikael, are you here? So if you could stop sharing.
Yes. Moment. How can I do that? Okay.
I'm here.
Great.
Yes. Let me. Okay. Stop sharing. Here. Okay. Right.
Okay.
So next we will hear about generating the full standard model at linear colliders from Mikael Berggren.
Yep. Okay, so can you hear me and see my slides?
Yes.
Okay, very
You're
good.
fine.
So then I will start. So I'm very pleased to have the opportunity to explain how we generate the entire standard model at linear colliders. And this is a talk on the behalf of the linear collider collaboration, in particular of the linear collider generator group, the LCGG. So this is the outline of my talk. I will first start with a few general words on linear colliders, then the main topic with details on process classification, generators for physics and beam properties, and the steps of the process. I'll make an outlook and then conclude. And as a disclaimer, I would also want to point out that this is not a talk about physics, the physics in event generation, or about detector simulation, if anybody thought that from the title of the talk. Okay, so linear colliders are E plus or minus machines with energies from the Higgs threshold or even Z pole up to the TV scale with the polarized beams. So in E plus or minus production, the production is electroweak, so this leads to low backgrounds, which in turn means that detectors have close to 4 pi coverage. They can be thin because they don't need to be red hard, and they do not need triggers. And in addition, since electrons are point-like, the initial state is known. So there are 2 projects. So it's the ILC and CLIC. And ILC is under serious political consideration in Japan, and CLIC is a possible future project at CERN. Okay, so the raison d'etre for linear colliders is precision. So we need excellent detectors and well-controlled machine conditions, but we also need matching background estimates. And this means that Monte Carlo statistics or missing channels must under no circumstances give major systematic uncertainty. So all channels must be generated and with the statistics well above the real data, and that the machine conditions must be well modeled. And in addition, at linear collider, all events are interesting and often fully reconstructed. So we can say that our mindset is more that of a B factor than that at LHC. And this generation effort has from day one been a common one between the different detector concepts and different machines, and it's been managed by the LCGG. Okay, so to generate the full standard model, what's the problem? I mean, you just select the generator and press return, right? Yeah, not really. I mean, there's lots of details. So what is it that collides? Is it electrons or photons? What is the exact energy and polarization of them? Where do they collide exactly? And what else happens apart from the physics event? So what are the machine conditions? And in addition to this, it's the physics itself. So as I already said, that linear collider, all events are interesting. See the examples here of the 8-jet TTH event at 1 TeV and the ZH event at 250. And we have a huge spread of cross sections, but for one analysis, it might be that the main background is from a tiny cross-section one, or in another, it might be that it's a tiny fraction of the huge cross-section process. And in addition, we want to group background sources in an intelligent way, and that's surely different for different analyses. So in essence, it's a good idea to separate channels in an intelligent and well-documented way. So how do we do this classification? Well, the first step is the initial state. So this can be E plus E minus, it can be E plus gamma, it can be E gamma, or it can be gamma gamma. And in addition, for the initial state, we need to know polarization and what type of gammas we have. Are they real gammas or virtual? Then we go on classifying by the final state, by the number of final fermions. It can be a small number like in this diagram, or a big number like in this 6 fermion case. And we want to generate everything from 1 to 8 final fermions. Then we also have a flavor grouping. So we can distinguish a typical WW 4-quark event like this one to a typical ZZ1 4-quark event like this one. This we also want to separate. And we want to separate whether the final state is leptonic, hadronic, or semi-leptonic. And we also want to separate special cases, like, for instance, T-channel dominated processes like this single W diagram here. And we need to avoid double counting, like, for instance, virtual gammas to 2 fermions as compared to E plus E minus to 2 electron positron and 2 fermions. These have the same final state, but generated in different ways. So our main generator for physics is Wizard. By the way, whenever you see a underlined word like this is a live link in the PDF. And well, WIZARD makes full matrix element evaluation, but only at tree level. But it can do polarized beams. It has full helicity treatment, full color flow treatment. It can handle the beam spectrum using the CLC2 program, and it can handle polarized tau decays using the TAULA program. And most importantly, it can do up to 2 to 8 processes. And this is actually then more important than next to leading order for E plus E minus. And here you see this diagram. So this is a 5 fermion diagram, and this is just one of these about 500 different tree level diagrams that gives rise to that same final state. So even tree level can be quite complicated. So WIZARD produces the hard interaction, and the subsequent partner showering hadronization is done by Pythia. And within the generator group, we have tuned the hadronization using the input from Opal at LEP2, being the highest energy really plus or minus data existing. So the definition of the processes is given in the steering file to WIZARD. It's called the Cinderin, which also drives the scripts organizing the production. And well, the people who know the Lord of the Rings sort of get the joke on this slide. So the Cinderin is actually a language, and we use its power to make sure that all processes are included. So we basically do using aliases and grouping, and then just ask WIZARD to figure out what are the processes corresponding. Okay, so let me now discuss the beam effects for a few slides. For the beam spectrum, first we have the incoming beam spread, which you can see in the right hand plot here, and this of course comes from the input from the machine design. But it also comes from beam effects due to the extremely tight focusing. This is illustrated in the cartoon down here. This produces a long tail in the spectrum, which you see in the left plot here, which is the same as the right hand, but on a log scale and a larger scale. So this tail is created by the beam-beam interactions. You also produce photons in the beam-beam interactions. So this we also have to know. So we need to integrate a beam-beam simulation into the system, and this is done with guinea pig, which supplies us with the spectra and the amount of photons, and it also shows us the distribution of the beam spot illustrated here. And in this plot, you see two different slightly shifted peaks, and this is the beam spot for E gamma, electron gamma, and positron gamma, and you see that the actual average beam spot is slightly different in the two cases. This also guinea pig can show us. Okay, we also get spurious interactions of two types. So we get pair background, which is pairs produced from photons in the very high fields, and this is illustrated by the guinea pig simulation of a single bunch crossing. We also have soft gamma-gamma events, but you should note that this is only around, on average, one low multiplicity per bunch crossing, so it's nothing to do with the LHC kind of pileup. So this, at this very low masses, the matrix element doesn't really work, so we use Pythia down to 2 GeV of invariant mass, and below this we have developed a custom generator to basically to fit to the data, which is shown here in the plot. So for both types, we create pools of events that are randomly picked and then overlaid to the physics events. For the low PT hadrons, this is rather straightforward. For the pairs, what we do is that we feed this through this fast simulation program SGV to pick the few events that actually would, or the few tracks would actually enter the tracking, which would be the tracks up here in the corner. The other pairs are hitting the forward calorimetry, and this distribution we use to create a background map of the occupancy in the forward calorimetry, which is fed into the simulation. Okay, so now for the organization of the process. So exactly the same wizard process definition is tasked to build a directory structure which ends up at a unique directory for each physics process. The code needed for each process is compiled, and the pre-evaluation of the phase space integrals is done, which makes it possible to mask out processes that actually have no cross-section. And then we do the full integration with an error goal of 1 per mil in the mathematics, and this is submitted to local batch form under Condor, and this goes for up to 5 fermions. This is an overnight job. We then do a pilot generation of all channels to be able to evaluate the resources needed for the full job. And at this point, we really have organized something and we are ready to generate the full standard model. So the generation, this is also done on a batch form. In most cases, we can run one process, a full generation of one process as one job, but in some processes, notably the 2 fermion runs, you can actually get up to 1 billion events. So this must be split in several jobs. So at the end of each job, the events in the LCIO format, which is sort of the common event data model for most of the plus minus, future plus minus machines, not only the linear colliders actually. And various auxiliary files are uploaded to the grid, and where the simulation and reconstruction direct system kicks in. And for the details of this, I recommend that you listen to Remedia's talk in the same track on Friday. So at this point, we can free the disk on the batch cluster, otherwise in this case might become an issue. Okay, then the documentation. So this is created on the fly by the generation job. The most important information you actually have in the event header for each event. So the process ID, beam polarization, and cross section. Then we have the generator metadata files, which condenses all the job specific information. This is actually browsable on the web, and once it's uploaded to the grid, it drives the detector simulation jobs. And finally, the full input and output of everything except the events themselves, of course, and including the diagram plots that I showed you in previous plots. These are also produced at this point. The integration, the results from the integration, and all this is also viewable on the web and in the form of a tarball, may also stored on the grid. Okay, so now for a short outlook. So soon we are planning to make a massive generation of the 250 GV stage of the ILC with a much bigger statistics than previously done. However, we still estimate that this can be done with the same model of running it on local batch farms. You see some numbers here in red. Furthermore, we will start exploring some new features in the latest version of Wizard, in particular using the Wizard integrated match partner shower machinery rather than doing this externally with Pythia. We also reckon that Wizard soon can do matching also between initial state and final state photons, and we wish to work out priority processes to develop electroweak next to leading order calculations. And in general, it would be nice to have other generators. We are following advances and other alternatives and or specialized codes. And in particular, Sharad is advancing in the direction to be used for linear collider. Okay, so let me then quickly conclude. So I explained that due to the precision requirements at a linear collider, Monte Carlo statistics must be sufficient. I showed how this is achieved by bringing many different codes together and fully scripting this and documented it in a physics-oriented fashion, and that the entire system pivots like around one single data source, the wizard process definition phi. Okay, thank you.
Okay, I think we have time for one question. Do we have any from the audience, including my co-hosts, if you just want to speak up? If not, I do have a question myself.
Yes.
So I'm trying to understand what your future computing resources will be. You gave us some hints in your talk. And from those, it sounds like it's minor compared to future LHC needs or even the intensity frontier neutrino people. Do you agree with that, or do you think that this is just the beginning and you will start to compete for computing resources going forward?
Well, this is actually a question more to Remy on Friday, because it's clear that this generation stage is not, as I say, we believe that even this massive production we are doing can be done on a local batch farm. We don't even need to go to the grid to do this. But of course, this is we're talking about a few milliseconds per generated event, not about minutes per fully simulated and reconstructed events. So this is more a question to Remy when he will explain about the.
Okay.
So so I do indeed think that the resources are resource needs are smaller than for high-dome LHC, but they are not negligible.
Okay. Well, I have one minor question, and that is you said that the number of final state particles is more important to you than the next to leading order. Is there some way you can explain that quickly? What is it about your physics that makes that true?
Well, I would say it's basically because we are this is electroweak interaction. It's not strong interaction. So
yeah.
So and the fact that you can produce, I mean, you have diagrams where you have up to 4 intermediate bosons. It's much more important than to know exactly what the loop corrections to that is.
Okay.
And the other thing is that contrary to what one spontaneous might think, next to leading order in weak interaction is much harder to calculate than in strong interactions.
I think I've heard that before. Yes.
Yes. So it's partly a necessity that there isn't so much full next to leading order calculations in available. It exists, but it's still sort of in the infancy compared to what is done for the strong interaction.
Okay. Thank you. So I think we go on coffee break now, and I think we're only a few minutes behind schedule, so let's reconvene at the scheduled time at 4:50 then. Thank you all.
Thank you.
Can you hear me okay?
Yes, we can hear you. Right, so we're going to hear from Nick Prouse on advances in simulation and reconstruction for Hyper-K.
Okay, I'll just share my screen. Can you see the screen okay?
Yes, well, it's in slide presentation mode. Yeah, there we go. Yeah.
Yep. So I'll start off with a brief introduction of the experiment. So Hyper-K consists of a huge water Cherenkov fire detector, about an order of magnitude larger than the existing Super K detector. And this will see neutrinos coming from various astrophysical sources. It'll search for proton decay, and it'll also see neutrinos coming from the J-type neutrino beam, situated around 300 kilometers away at the other side of Japan. There'll also be a suite of near detectors.
So, Nick, sorry to interrupt. I had lots of Zoom windows open, and I didn't notice when you first started that your slides are cut off on the right-hand edge. So we can't actually see the text in, or we only see half the text. Is there a way you can zoom so that the full slide is shown?
Let me try to readjust the window. I'm not sure why that's happening.
Yeah, I don't know either. Graeme, do you use Google Slides all the time? Do you have any advice?
I don't know, because I always download PDFs to
Okay.
present with.
I see.
I could quickly load up the PDF and see if that helps.
If your what you try next doesn't work, then let's go ahead and try that.
So I'll put this in full screen and just let me know if it.
Okay.
Can you see that okay?
It's still getting here. We don't have it yet.
Still not showing, or?
That's right. It's still not showing. Maybe we better switch to the PDF strategy.
So I've loaded the PDF now, but I guess you're not seeing that.
I don't see the PDF. I see you, so I think it's just that your screen share isn't coming through.
Maybe I'll try, sorry about this, stopping and restarting the screen share.
Yeah.
Can you see the screen now?
We do see the screen, but it's again clipped pretty much the way it was before. That's interesting. Huh.
Can you just share the browser window and not the whole desktop?
It doesn't.
Or the PDF viewer?
The option. When I choose to screen share, it seems to only give me the option of the full. The full desktop or whiteboard. The only options.
Okay.
I could try and resize the window to fit it.
Yeah, let's try that.
I'm not really sure where it's cutting off, but.
Okay, it's better now. Could you go to the next slide and let's see. It's better. I think in the interest of time, we'll go with this. How about if you get rid of the slide sorter pane? That might. All right, let's just go with this. It's much better than it was.
Okay, sorry about that.
Mm-hmm.
Yeah, so I was just saying that in addition to the fire detector, there's also the near detectors of the similar to what the T2K experiment has, and also a new intermediate water Cherenkov detector, which will be a much smaller water Cherenkov detector, about 1 kilometer from the source. So as I mentioned, the far detector of Hyper-K will be about an order of magnitude larger than Super-K. It'll actually be the third generation of water Cherenkov detectors in Kamioka, with each generation getting much larger, having a much larger number of PMTs, and also improved PMT technology. So we'll need new simulation and reconstruction to make the most of this, and to be able to draw out as much physics as possible. An additional new photosensor technology that's being looked at for the far detector, but will also be needed for this smaller intermediate detector, is these multi-PMT modules. So these are designed to use a number of smaller PMTs to get better timing resolution, better position resolution, and also get some directionality information. And these are needed for the smaller size of the intermediate detector in order to get the precision measurements needed. So the intermediate detector is, as I mentioned, a smaller water Cherenkov detector which sits in a vertical pit. It's able to move up and down inside this pit, and that's so that it can measure the neutrino flux coming at different off-axis angles from the neutrino beam, so that it can measure different energy spectra of the neutrinos to measure the flux and cross-section in a way to reduce the systematic errors in the far detector. So moving on to the software side of things. So we have a pretty standard setup for our software. We have our detector simulation, which is a unified simulation package for both water Cherenkov detectors with the flexible ability to use different detector designs. And then this will lead in, along with our real data, into various different reconstruction packages. So we have separate reconstruction for low energy and high energy. And we're also looking at new machine learning techniques to improve our reconstruction. And then this will go into our analysis. Something that we've developed more recently is actually taking the trigger and DAQ simulations out of our detector simulation and instead using this open source framework that's been developed so that we can have the same code that's running on our hardware that runs in real time for our actual data to also run on our simulated data. So onto the simulation software. As I mentioned, we have a single simulation software called WCSim for water Cherenkov detectors. And this is designed to be flexible and able to do detector designs, different detector setups, to have a unified framework across the different detectors, as well as being suited to detector optimization studies to change the detector design and make sure we're getting the best detector, building the best detector possible. So once we've given our detector geometry and our PMT and electronic specifications, we tell the particles to simulate. It simulates propagates the particles through the tank, producing the Cherenkov light, propagates the Cherenkov photons, and simulates the PMT detection of those photons and the electronics. So then we end up with our output, which is the digitized PMT hit times and charges, in the same way that the real detector would give us in our real data to feed into our reconstruction software. And of course, we also get our truth information to use for debugging and tuning the reconstruction software and further analysis. So here you can see some examples of events being simulated in this software. This is for the Hyper-K far detector. So on the left, we've got a nice muon ring along with the incoming neutrino. And if you zoom in there, you can also see the tracks of the other particles that are simulated in the simulation. On the right, you can see an event display type image showing an event which actually demonstrates how we've got our implementation of both the inner detector, that's the PMTs facing inwards towards the tank, as well as the outer sector, which has PMTs facing outwards, in order to veto incoming backgrounds such as cosmic muons. And here's some examples with the intermediate sector. Here you can see the multi-PMT simulation. And this is actually two different designs for multi-PMTs to optimize that design. We're also looking at different designs for the detector itself based on the size of the detector. And here you can see how these multi-PMTs give a much greater granularity of what's happening in the Cherenkov ring. So moving on to the reconstruction software, starting off with the low energy reconstruction, we use a package called Bonsai, which was originally developed for Super-K, and it starts off by fitting the vertex position of the event, and this is all based on the hit timing. So it tries to maximize this goodness variable, which is based on the timing residuals, so that's the time that we observe a hit in a particular PMT relative to the time we expect that PMT to be hit, given a candidate vertex and the expected time of flight of a photon in the water. So once we've got our position, we can also then reconstruct the direction using the pattern of the Cherenkov cone and the energy based on the number of hits observed compared to the number of hits you would expect to see at each PMT, given a particular energy. So something we're moving to now is shifting towards a new package called Leaf, which uses currently the same algorithms as Bonsai, but in a much more modern and flexible framework. This is making it much easier for us to tune different detector geometries and perform the detector optimization studies that we want to perform. So here's an example of such a study. So this is for the Hyper-K FAR detector, looking at different photo coverages, different numbers of PMTs in the tank, as well as different assumed dark rates for those PMTs. And we can see how the vertex resolution changes based on these different designs. On the right, we have a similar study, but looking at, again, the number of PMDs, but also with or without the addition of multi-PMT modules. So it's very easy to perform these studies with our unified simulation and reconstruction software. And we can see that basically we get pretty good resolutions as we would expect. But the most important factors here for low energy is increasing the total photo coverage of the detector and making sure that the dark rate is low enough to increase our signal to noise ratio. Moving on to high energy, this is using a much more involved algorithm that was again originally developed for Super K, although based on an algorithm that was originally for Mini Boon. And this is using the full likelihood information of both the time and charge of all the hit PMTs, as well as the unhit PMTs. So these probabilities and the probability distributions for charge and time are based on both the direct light coming from the charged particle, as well as the scattered and reflected light. And so by maximizing this likelihood, we can find the best fit position as well as direction and energy simultaneously. If we do this for different particular particle hypotheses, then we can compare the likelihood ratios to determine which type of particle the event appears to be. An example of this is for the pi-0 background. So this is a background to the electron-neutrino signal used for our oscillation analysis. And the pi-0 can look very similar to an electron because it decays to 2 gammas, which if the opening angle between those gammas is small, both gammas produce electromagnetic showers, which look very similar to electron rings. And if those rings are overlapping, it can look like a single ring electron event. So FitCoon, the Heinz reconstruction, will maximize the likelihoods under 2 hypotheses, under the single ring electron hypothesis and the 2-ring pi-0 hypothesis. For this pi-0 hypothesis, it will try to reconstruct the mass of the pi-0, and then we can just do a simple 2D cut on the likelihood ratio of pi-0 versus electron and the reconstructed pi-0 mass. And you can see this does a reasonably good job of removing this background. Also looking at the intermediate detector, we can start to do some more of these detector optimization studies. So here we're looking at different designs for the intermediate detector using either 20-inch PMTs, 8-inch PMTs, or the multi-PMTs. And as you reduce the size of the PMTs, you expect to get better performance, which is what we observe. But what's interesting is that these multi-PMTs, even with a smaller percentage of the tank actually covered in PMTs, we're still getting improved particle identification and improved vertex resolutions. So this suggests that it really is using all of this additional timing information, additional spatial resolution, but perhaps also the directionality that these multi-PMT modules provide. So the final part of the talk is about the new machine learning reconstruction, which we're currently developing. So for the traditional reconstruction methods, we're starting to reach the limit of what we can do. If we want to start to improve, if we want to continue to improve our resolutions, then we need to start to remove some of the assumptions that are being made in the physics model of our reconstruction algorithms. This leads to more complex likelihoods, and already having a detector with more PMTs for our FAR detector than we're used to using, the computation time is actually becoming a seriously limiting factor, with events taking minutes to reconstruct. So machine learning is being used throughout HEP now for reconstruction purposes. And here there's really a lot of potential to both improve on our resolutions and improve on the performance using much less computation time once these networks have been trained. So we've started this WatchMal group, which is Water Cherenkov Machine Learning, which is a collection of people across different collaborations working on Water Cherenkov detectors to explore machine learning for Water Cherenkov reconstruction, as well as people from actually other detectors as well, including water-based liquid scintillators, which also have some common challenges. So one of the things we need to deal with is how to appropriately deal with the cylindrical shape of the tank, which is not necessarily suited to some of the more traditional machine learning architectures, and also dealing with high resolution and often quite sparse data. So obviously our physics goals for this are just to improve our precision of the detectors, improving the reconstruction resolutions, and start to discriminate different particle types that is more difficult to do using traditional techniques, and also improve our detector calibration and systematics. So I don't have time to go into all of the various studies we're doing, but I'll just pick out this as an example. So this is using a convolutional neural network to classify different particle ring types. So here we're using electron, muon, and gamma single ring events. And this is for the intermediate detector. So we've unwrapped our cylinder in a fairly naive way just onto a square image, and then passing this into CNN. And comparing the classification performance of muon versus electron to FitCoon, we see that across almost the entire energy range, we're actually seeing significant improvements now. Another thing that we can do with this CNN, which hasn't been possible before using the traditional reconstruction, is some statistical separation of gammas versus electrons, which look extremely similar by eye and are very difficult to distinguish. But this is important because the neutral current single gamma events can form a significant background again to our electron neutrino oscillation appearance sample. So that's all quite promising. As I mentioned, there's lots of other things we're investigating using machine learning. We're looking at reconstructing the energy and position and other physical quantities, which is implemented and is working, and it's looking quite promising, getting similar resolutions at the moment to FitCoon, but further work needs to be done to do full comparisons to the existing reconstruction. We're looking at different architectures that might be more suited to the cylindrical shape of the detector. So we're using either point cloud neural networks or graph neural networks. Both of these have been implemented, and the point net is looking quite promising. And we're also looking at other methods, if we are to stick with the CNNs, the methods of unwrapping the cylinder to more appropriately use the geometrical information of the position of the PMTs. Some other things we're looking at is generative networks. So one way we could use these is to actually combine them with the FitCoon likelihood type analysis, so that the network would generate our likelihoods rather than relying on some physics model with assumptions to generate those likelihoods. And then we would put those machine learning based likelihoods into the standard FitCoon likelihood fitter, and combine both the traditional methods with the modern machine learning methods. And we're also looking at using generative methods to improve on our detector simulation, and improve our detector systematics. So in summary, we have a framework developed to provide a consistent simulation and reconstruction software for both of our water sharing gov detectors, and making it easy and making it flexible so that it's easy to adapt to different detector setups and perform the design optimization studies. Our reconstruction packages are giving good resolutions, exploiting the advantages of the new photosensors, and enabling the smaller intermediate detector to perform precision measurements. And now we're looking into using machine learning to improve on our resolutions and allow new types of analysis. Thank you.
Okay, thank you. We don't have a lot of time for questions, but does anybody have a quick one? Yeah, I'm afraid we used up a lot of your time with the technical problems. But thank you very much. Oh, we have one. Good.
Yeah, okay, sorry. Yeah, could I maybe ask a quick question, Nick? So I was interested to know, moving from Super K to Hyper K, how do things scale? I mean, does the simulation go like somehow the volume of the detector, but the reconstruction, like the surface area of PMTs that you have? So what's the challenge of Hyper K compared to Super K?
Yeah, so the simulation time, in terms of simulating the actual particles inside the detector, is roughly similar. Obviously, there's a bigger volume, but that doesn't matter too much so long as the number of particles being simulated is roughly similar. But on the simulation side, the number of PMTs and number of PMTs being simulated will make a difference, but it's not too much slower. For the reconstruction, though, for the traditional reconstruction methods, the number of PMTs does make a big difference, especially for the high energy reconstruction where we're using all of the PMTs in the entire detector. And so this basically does scale by the number of PMTs, and that's where we're starting to see issues with the performance of sort of computation time of reconstructing with Hyper-K.
Here is Graeme, who will be talking about detector simulation upgrades for HL-LHC. So,
yep, so let's start sharing. Okay, sharing okay?
yes, it looks fine.
Excellent.
Go to the next slide, though, just to check. Yes,
okay.
fine.
Okay, so thanks very much for everyone's attention. Today I'm going to talk to you about some of the work which is mainly being done in the SFT group. We'll all touch on things which are happening outside of our group about improving the performance of detector simulation, particularly oriented at high luminosity LHC. So for high luminosity LHC, I'm sure this is no strange topic for the people who are in this session, but we will know that we will see a big increase in the beam luminosity and a very large increase in the pileup for Atlas and CMS. And the goal over the lifetime of high luminosity LHC is to collect about 3 attobarns of data. So that's a massive increase in the amount of data that we have to study Higgs physics, flavor physics, dark matter, the whole of the LHC program. And it's about 20 times more data than we have today. So this, of course, lays down a big challenge for simulation, because all of this beam data means that we need more simulated data to support the analysis that we would like to do. Okay, so here, I'm not going to go through this in detail, but it's just to sort of highlight what the anticipated simulation needs are actually going to be. And they all come down to the fact that GEONT 4 and the detailed particle tracking is highly CPU intensive for almost all of the experiments. And as I said, as the the experiments anticipate taking more and more data, there's a consequent need to increase the amount of simulation that you have in order to match that data. Okay, so turning to simulation software, of course, the cornerstone of simulation for the LHC is GEONT4. And this was a toolkit which was born in the late 1990s, and it provides a highly flexible framework written in C++. And I think it's been a huge success for the LHC. It allowed progress in physics by allowing us to compare different models, competing models in the same energy ranges, and allowed complementary models to be combined so that we were able to cover very large energy ranges. And that delivered a physics precision and, let's say, an understanding of the simulated data that allowed a very rapid physics output from the LHC experiments. And we know that the corpus of papers that the LHC experiments have produced has really pushed the boundaries of our understanding inside of high energy physics. So GEONT4, as a collaboration, of course, has a mission to provide production quality simulation software for the experiments, to maintain the software which is already there, while hopefully evolving the toolkit to be more sustainable, improving the physics models with better precision and energy range extensions, particularly in hadronic physics. There are a number of improvements which are envisaged. But what I will mainly talk about in this talk is how we improve the overall computational performance of the simulation. So just to underline again, this is sort of like slightly less information on this slide, but maybe we focus in on how we bridge the gap. Now we have the advantage in simulation that by and large, we don't mind too much about the pileup, although we do have to care about it at the digitization step. But it is going to scale with the event rate, which for Atlas and CMS will be about a factor of 10 increase in the trigger rate for high luminosity. And that puts a lot of pressure on the computing budget. And one can see, if one does the various studies that Atlas and CMS have managed, that running today's full GEONT4 simulation for the needs of high luminosity LHC would simply not be affordable with the kind of technology increases that we expect to get in computing. As we know, we're well beyond the level where Moore's law would simply deliver more and more performance every year. So the challenge then is to make simulation faster without sacrificing the relevant physics accuracy that we need to support the physics program. And I should say that the strategic development model that we have for GEONT4 is to recognize that it's crucial production simulation software for the experiments, and therefore changes must be able to be introduced adiabatically. You know, we're running experiments and we continue to take data with run 3 starting not very far from now. And so the best things that we can do are ones where we can take improvements and we can introduce them into GEONT4. Now that doesn't mean freezing the GEONT4 code base, rather it just means combining, I think, in a clever way, the different codes that we use so that they become faster and better for the physics program that we have. So if you delve into that a little bit more deeply, one sees 3 tracks for improvement. So there's a kind of 3-pronged approach, if you like, towards improving detector simulation. The first one is maybe the least dramatic, but the one which can probably gain us a good amount, which would be very useful, and that's optimization of the current GEONT4 code to run faster. And in the next couple of slides, I'll talk a little bit about GEONT-V and why we think we can actually get the current GEONT4 code to run faster. This is mostly work which is internal to GEONT4. Hopefully it has little direct impact on the user code. So in a certain sense for the experiments, this would just be like free improvements. The second track is fast simulation. We know all of the experiments use this technique already. The idea here is you replace the detailed particle tracking models with different methods, so parametric responses or more and more machine learning techniques are becoming a very hot topic. here, and we know particularly for the slower subdetectors that you probably want to increase the amount of fast simulation that you've done, as Adam and Matteo already talked about for LHCb in particular. And then the third prong is, let's say, hardware revolutions. So these are partly evolutions, partly revolutions. I think those of us who keep a watch on the hardware market for computing are noticing that there's an increasing trend away from purely CPU-based machines. And in particular, GPUs are becoming more and more common for sort of computationally intense problems. So these are not particularly easy to use with our current simulation software, but I think there has to be an active R&D program to start looking at how we could use these machines for the detector simulation in high energy physics. So, if I can work out how to flip the slides. Yeah, let me segue a little bit into the Géant V prototype. So this was a very interesting set of R&D which was done, and it particularly focused on how we could use vectorization, particularly on CPUs, to improve the performance of particle transport. So there was a prototype developed that had pretty complete electromagnetic physics, and the idea here was that you would use baskets of particles to gather the work of similar particle types in similar volumes into CPU vector register lanes. And there's recently a very nice paper has been uploaded to the archive, which gives a careful comparison to Géant 4. And you find in that paper that you can get up to about a 2 times speed up observed, although this is highly architecture dependent, in fact. I'll talk more about that on the next slide. But the Géant V prototype actually already delivered improvements into the current Géant 4 code by developing libraries which were more optimized for modern hardware. So these were the VecCore, VecGeom, and VecMath libraries. And let me just remind you that things like VecGeom were actually able to deliver very substantial increases in the geometry performance that we would get inside of simulation. So these were very worthwhile improvements which were made. Okay, so where did this factor 2 speed up come from? That's a very interesting question. And it seems that the main speed up factors that we got were in better use of the caches. So the data cache usage improved in Géant V, and the instruction cache usage improved as well. So data cache meant that we were doing more things with the same kind of data, so that the data wasn't falling out of the cache. And the instruction cache usage was as a result of simpler code, which had fewer classes in it, less indirections, and less branching going on. And I think that explains why the speed up which was seen with Géant V was so dependent on exactly which architecture of processor that you were using, because it was very dependent on how that CPU delivered the cache infrastructure. Now, what was a disappointment in Géant V was that the vectorization impact was much smaller than what was hoped for. Only a small fraction of the code could really be vectorized or run efficiently in SimD. And I think what was found was that the overheads of reshuffling data, so this basketization so-called, really cancelled out the gains from vectorization in a lot of cases. So although the basketization did bring benefits for floating point hotspots like the magnetic field and the multiple scattering, overall the improvement from vectorization was relatively small. But the improvements from using the cache and both the data and the instruction cache better mean that we can be pretty confident that by rewriting and modernizing parts of Géant 4, we could actually bring tens of % of speed up by compactifying the code, using better data layouts, and reducing the virtual function calls. So definitely gains to be made there. So if you want to improve Géant 4, well, what does it actually look like? So I've given on this slide a flame graph that shows CMS simulation using Géant 4. And the flame graph, this is basically printing out the call stack vertically at each point in time, which is the horizontal axis. So the fact that you see very short, narrow spikes means that the way in which Geant4 code runs is it makes lots and lots of very deep function calls, which go and do one particular thing and then unwind. And it's clear that this kind of profile puts a lot of pressure on the instruction cache. And this is compounded in multi-threaded Geant4 by the fact that all of the threads are acting independently of each other. So a thread might be following one particle and calling the geometry, another one might be calling physics, and there could be many different physics processes. Another one is doing the magnetic field. But a lot of the cache infrastructure on the CPU is shared, and this is very expensive. So there's R&D on sub-event parallelism that we hope will help alleviate this, being led by Jonathan Marsden at Berkeley Lab. There's also one of the improvements in monitoring the performance of the current code is to dig into a little bit what the CPU performance registers can tell you using perf. And here there's very nice infrastructure which is being developed, which will actually tell you what the performance changes were in each of the Geant4 function calls. So here I just flash up an example where you can see that between the current master branch of Geant4 and the old 10.5 release, there were significant improvements in the Geant4 physics vector value, but some definite degradations in the electromagnetic process, getting the physical interaction length. So making this a regular part of the way that we run Geant4 will actually help us keep a very close eye on improvements and regressions through the evolution of the code. And I should mention in passing that these things are very much tied together. So it's not true that these things are completely factorizable to one function. You improve one particular function and you might actually bump some degradation into the next function down the stack. Okay, some of the improvements which are foreseen though are taking full advantage of what we have in VecGeom by improving the navigation. And without going into too many details, we already can foresee that we might get gains of between 8 and 17% over the current Geant4. And another one is to do alternative transport. So this is really an attempt to focus on a particular area where for HEP, we don't need the full generality of Geant4. And we build a kind of super physics process, which would reduce the number of function calls that would be needed enormously. And essentially have a simplified physics framework. So what's being targeted is really electromagnetic physics that we know is particularly expensive for the HEP experiments. And if we can do that, we feel confident that we could probably provide some fairly significant speed ups for HEP at the cost of a generality that maybe we don't need for this particular area. Okay, let me talk a little bit about fast simulation. Now, as we already saw from the very nice examples from LHCb, fast simulation is usually experiment dependent, but that doesn't mean it can't be properly supported inside of Geant4. So there's work which is ongoing to streamline the procedure for using fast simulation to be able to extract the hits from the full simulation more easily and to be able to plug in a fast simulation model rather more easily, so that you should be able to import any model into your Geant4 stack, howsoever trained. And that means that experiments can spend more time on the precision of fast simulation and less time worrying about the integration of fast simulation. A couple of other things which are going on is a complete revamp of the GFAP Flash implementation inside of Geant4. This is rather an old fast simulation model, but we now know that we can improve both the speed and the accuracy of that implementation to the extent where it could be of interest to the experiments. And trying out different neural network training methods. So one method which is quite interesting is autoregressive functions, because these are scalable and rather stable. And we already have events that we can generate using that technique. So that will be moving into more of a full validation in the very near future. But let me, in my last couple of minutes, talk a little bit about compute accelerators, so the third prong of our attack on computing performance. So it should be pointed out that this is not particularly easy or obvious. General simulation of particle tracks is not a very natural candidate for GPUs. It has complex physics, so lots of different models. It's branchy, and there's lots of special cases. You don't know exactly what the workload is going to be due to the fact that it's a stochastic simulation. But as I said in my introduction, GPUs as a resource become more and more common, and the year-on-year performance improvements really outstrip the x86 CPUs by quite a margin. And we know that in medical physics, optical photons and neutron transport, there are already successful projects to use compute accelerators. So I think the key thing for us as high energy physics is to look for a problem which limits the scope so it's tractable, but is computationally intense so that the benefits could be significant. Concentrating on one particular physics area, learning how to deal with the evolution of different particle populations. But I think one thing we know is we have to stay on the GPU for all of the key operations. So if you go back and forth to the GPU lots and lots, you're going to be killed by the data movement time. So you want a good chunk of things which are done on the GPU. So some R&D prototypes that I think are pointing in the direction of how we could do this are really to sort of focus on the kind of electromagnetic calorimeter simulations. And we already have R&D that shows that we can upload geometries onto the GPU and use that for doing ray tracing, as seen in the top right-hand corner. And actually recent work is demonstrating how one can optimize these kind of workflows for GPUs. And one of the things that we noticed was that we weren't using the GPU very effectively because we were using too many registers in the kernel. And that by optimizing the use of the registers, we could get a factor 35% improvement. But splitting the kernels up to be smaller would give us an even bigger improvement there. So it's nice to see that that kind of detailed performance optimization on the GPU is happening. And another project which I think is very important is looking at electromagnetic physics on the GPUs. And I think the key processes to get in here are pair production and Bremsstrahlung. And that allows us to test how we can manage mutable populations on a GPU. We know we don't want too much sorting because the overheads will kill the performance, but somehow we want to limit the divergence of the warps and cut event tails. And so you could combine the work for the geometry with the electromagnetic physics, and then the idea is to recombine these different R&Ds into a computationally realistic example. So there's some very interesting R&D which is going on there into how to do detector simulation on GPUs. So let me draw my conclusions. So high luminosity LHC is a huge physics opportunity, but is a big challenge for detector simulation. We need our production simulation to become faster to cope with the greatly increased event rates. And a three-pronged approach is envisaged, where we internally improve the current Geon4 toolkit to become incrementally faster. Easier integration of fast simulation methods and techniques where we want to apply these, and a very interesting R&D program for non-CPU devices, particularly GPUs. So that's a very active area, and we very much look forward to seeing these activities come to more fruition over the next several years. And I think that's an appropriate point to stop. So thanks, everybody.
Well, thank you, Graeme. I will call for questions now. Does anybody have any? If not, I could ask one. I was intrigued by your slide number 10, where you said that the spikiness of this plot, I don't think I've ever seen it before, is the idea that you want to squish it down, flatten it, these spikes?
Yeah, I think there's really, this relates to two things. First of all, you want to squash it. So you want to find the most computationally intensive parts of this and reduce the number of calls that you need to make to do that. So that relates very much to this kind of mega physics process that you might want for electromagnetic physics, where you would bundle all your electromagnetic processes into something that Géant 4 would see as just being one thing. And I think we know which physics pieces we want in for the calorimeter simulations in HEP, and that would improve things a lot. And the second area where you want to improve that is you want to stop different threads from doing different things.
Yeah, that's your last bullet, right? And I was wondering about that because
exactly.
How do you do that without basketation or, you know, some sort of aggregation ahead of time?
Right. So I think that the way in which you want to try and do that is because you can, with the sub-event parallelism, you can get each thread to work on a different thing coherently. It's sort of basketization, but you don't have to reorganize your data structures. So the idea is just to make each thread proceed coherently so that every thread is doing geometry calls at the same time. But as I said, without having to reorganize the data. So it's still R&D, but it would probably help the instruction cache a lot. And we know that the instruction cache gets hit very hard in the current Géant 4.
Right. Okay. I look forward to results from that then. Good.
Excuse me, may I have a question?
Sure.
Just which of these remodeled forms of Géant would be the most suitable for running on the grid in the times of HL-LHC?
That's a really good question, Dagmar. And if I knew what the grid would look like for high luminosity LHC, I'd probably be able to give you a much better answer.
What about run 3?
Right. Well, for run 3, I think the grid is going to look very much like it looks today. Although
I think it might have some GPUs on it, right?
That's exactly what I was going to say. I think that what we're going to see is a gradual increase in the number of resources where you have GPUs available. And I think that is one of the reasons why the R&D in GPU work is very interesting, because we don't know how fast we'll be able to get detector simulation to work on GPUs, because it's a tricky problem. But we do know that we will get more and more machines where GPUs will just exist. So even if we don't use them very efficiently compared to LinPack, if we can use them at all, that's a big win for high energy physics. So I think that overall, what we're going to see is a strategy where one makes more and more use of the GPU, but one tries to do that in a flexible way. So if I land on a node, no GPU, fine, I can just do traditional CPU. If I find a GPU, great. If I can move the electromagnetic calorimeter onto the GPU, I would be very, very happy if we're in that situation by high luminosity LHC.
Okay, thank you.
Okay, so we're a bit behind, but I propose that we make up for that by just taking a 10-minute break and starting back at, well, it would be 10:50 my time, but it would be 17:50, I think, in European time.
Yep, that's right.
Okay. See you then. We're going to hear from him about computing for DUNE's long baseline neutrino oscillation experiment.
Great, thanks, Liz. So yes, I'm Mike Kirby here for the DUNE collaboration, and I'll talk to you about computing for DUNE. So to give you a quick outline, I'm going to give you an introduction to the DUNE experiment and our physics goals, talk to you about the near and far detector designs, and the impact that the size and scope of those detectors has on our computing model. Talk to you about the proto-DUNE detector at CERN, which is shown right here in the bottom right. and how all of this comes together to give DUNE some very unique computing challenges, a description of our computing model to address those challenges, and then the performance that we've had running on the proto-DUNE data itself. So a quick overview of the DUNE experiment. So DUNE is a neutrino experiment looking to measure neutrino oscillation parameters, things such as mass ordering, matter versus antimatter, asymmetry, potentially unitarity within the neutrino sector. But then also going beyond that and doing physics for proton decay, supernova neutrinos, and many other things. The experiment design itself is constructed of three major components: the neutrino beam production, shown here on the right at Fermilab, a near detector, also on site at Fermilab, and then a far detector, which consists of 4 liquid argon TPC modules that are 4,850 feet underground in Leeds, South Dakota, at the Sanford Underground Research Facility. The baseline for the experiment is 1,300 kilometers. And as well, the neutrino beam has been optimized for oscillation measurement sensitivity. So a little more detail about the far detector to give you some some scale for how large the detector is. This is a diagram of the cavern that is being constructed right now at the Sanford Underground Research Facility. It's going to have 3 caverns. The 2 caverns on the outside will contain the 4 far detector modules, and then the central cavern is where all of the service utilities, cryostat, cryogenic supports, facility support infrastructure will go. Looking in more detail at one of the far detector modules, you can see right over here on the right. And then again, to set scale, here is an image of a person standing at the lowest level of the cavern and exactly how large the far detector is. What does a single phase liquid argon time projection chamber look like? It is defined by a cathode plane and an anode plane, and then the drift volume. For us, the far detector at DUNE is going to have anode planes that are constructed of wires at 3 different angles, 2 of which are an induction plane and 1 is a collection plane. What this does is this gives us high spatial and calorimetric resolution, and this is important for our particle ID in order to distinguish between muon neutrino interactions and electron neutrino interactions, but then also very important in giving energy resolution for those reconstructed interactions, which are important when trying to determine L over E for the oscillation parameters. The image that I show you on the right is raw data from a liquid argon TPC, where on the x-axis we have the wire number, and on the y-axis is drift time, and you can see the excellent resolution for this interaction that is shown here. I should note that the drift time is set by the electric field. The sampling rate and the ADC precision at the anode wires is set by the physics goal and also by cost. So what does the final far detector design look like for the single phase liquid argon TPC? So it's a 17 kiloton liquid argon cryostat. It's got 150 anode plate assemblies tiled on center and on the walls. And here's an example of one of those anode plane assemblies. There is the choice is for 180 kilovolt electric field across each drift volume, which gives us a 5.4 millisecond drift time from the cathode all the way to the anode. So that is the maximum amount of time that it would take an electron, ionized electron, to drift from the cathode to the anode. And that sets our readout time for our beam triggered events. As well, we've chosen a 12-bit ADC that is sampled every half a microsecond, 2,560 channels per APA. When you combine all of this together, you end up with a 6 gigabyte uncompressed event coming out of one of the far detector modules. With about 5,000 events per day coming in on the beam trigger, this ends up being about 5 to 10 petabytes per year per module. Of course, this is just for the oscillation measurements that we want to do. There are also other physics that we want to achieve. So we do have to have time extended readout windows for our far detector modules that go beyond that 5.4 millisecond drift time. And those are going to be used for us to understand potentially supernova events with a continuous readout stream, calibrations, and other things. And the DAQ has been designed with a bandwidth large enough to handle that continuous readout, but at the same time, we are going to reduce this with utilizing our trigger, zero suppression, and compressed data format. And the end goal of all of this is about 30 petabytes per year from the FAR detector, with it dominated by a combination of calibration data, time extended readout windows, and then beam triggered. So what do we have to do with this actual raw data that's coming out of the liquid argon TPC? Well, we have to take these raw signals that we can see up here at the top, and then we need to run our reconstruction over it to remove noise, deconvolve the raw signals on the wires, and then look for the reconstruction of hits and objects inside of that. While these objects are spatially independent within an anode plate assembly, the signals on a given wire are actually dependent are not necessarily independent, and so we actually do require a 2D deconvolution and fast Fourier transform in order for us to go from the signals that you see at the top to the hits that you see at the bottom. And at the same time, we also have a single trigger record that can generate multiple events because we have spatially independent events across such a large FAR detector module. And this comes into the part of our data model because we need to break down this large 6 GB readout into much smaller events that we can then send out for processing out across our distributed computing. Going back a little bit and discussing those time extended readout, the FAR detector is designed to be sensitive to nearby, say, the Milky Way neighborhood supernova events. And these are estimated to occur every 30 to 200 years. But at the same time, we are going to tune our detector to have a false alarm rate about once a month so that we can continuously exercise all of the infrastructure that is needed to read this out. One of the questions is how long do we read out our FAR detector and take out of the continuous readout stream? So right here on the top right, I have a plot from the CERN Courier in January 2007 that shows the neutrino event distribution for supernova 1987A. And as you can see, the time of the neutrino events goes all the way out to 12 seconds. As well, the energy is between 10 and 40 MeV. So what we are looking at is a distribution of neutrino events across at least 10 seconds, but we're going to want to go farther than that. So if we actually look at our prediction for different aspects of the supernova explosion, we can have different aspects of the model occurring at different timescales. And so you can see that we want to be going out to at least tens of seconds. So and we're going to extend beyond that to 100 seconds to make sure that we don't miss anything. Of course, what does a 100-second readout for such a large detector end up coming to for data volume? So one channel would be 300 megabytes, one APA would be 768 gigabytes, a module 115 terabytes of uncompressed. But if we take all 4 FAR detector single phase modules, we end up with about 180 terabytes compressed using the current estimates on how much we can zero suppress and compress our data. Of course, how do we get all of that data up out of the cavern? We're going to need a relatively fast network so that we can get this out quickly and transfer that data out within 4 to 5 hours, because it's important for us to detect and process that data so that we can then give information for multi-messenger observations that follow up. We have constructed proto-DUNE detectors at CERN. So these are small single phase and dual phase liquid argon TPCs, small in the sense that they are not the full FAR detector. They're about 11 meters tall. The single phase is constructed with 6 APAs instead of the 150, and the dual phase was constructed with 4 charge readout planes. And we're going to utilize the data that we collect from these to understand how well our computing model matches up with what kind of performance we can actually get right now. An important thing to note is that right now, the single phase proto-DUNE is being decommissioned and drained of liquid argon while the dual phase is being refilled, and the operations is going to start back up in Q3 of 2021, and then we're looking to take more beam data in 2022. Of course, there's also the near detector design. This is a critical part of our oscillation analysis. It's going to give us precise cross-section measurements to improve our modeling. But it is also a very unique design. So it is the combination of 3 different detectors, a liquid argon TPC, a multi-purpose detector, and then a beam monitor. But then additionally, on top of that, the liquid argon TPC and the multi-purpose detector actually move move off axis so that we can get a spread of the beam. The readout we anticipate is about 1 hertz, and we're going to be getting about 1 petabyte per year, but it is likely much larger than that. And one of the interesting things is there's a greater simulation complexity having all 3 of these different detectors there, but then also having them move, and also the need for statistics is much greater than compared with the FAR detector, where we only anticipate about 5,000 events per day. Here, this 1 hertz readout is much, much higher. So adding all of this together, what are the computing challenges for DUNE? One is we need to transfer and store 30 petabytes a year from the FAR detector at SURF. We need to be able to handle the burst of transfer and processing from these time extended triggers, specifically supernova. It's about 180 terabytes. Right now, our estimates is that we would need 30,000 CPUs to analyze the data within 4 hours and provide 5-degree pointing resolution for follow-on for multi-messenger observations. But another challenge that we have is the creation of ROIs after our signal processing and noise removal, and reducing the data volume from 6 gigabytes per event for something that is much more manageable, so that we don't try and transfer 6 gigabytes around the computing grid around the world. And then we also have calibration data, which is similar to the supernova. The near detector data volume and simulation are all going to be great challenges, especially when we have to get down to a 1 MeV scale for the FAR detector, and then the very high occupancy for the near detector. So what is our computing model that we're going to use to try and accomplish these goals? So we are working from the HSF DOMA model for our sites. So the idea is that we have 5 different types of sites. We have an archive center where we do tape storage and staging. We have a data center with disk and CPU, a compute center, which is just CPU and a small amount of cache, an analysis facility, which is again, CPU and cache, and then potentially utilization of what is referred to as ephemeral facilities, which I think of as HPC and inference as a service, things out on the cloud. Our goal is to have our resources split between Fermilab and other institution of 25% and 75% across all of this. At the same time, Fermilab is planning to store 1 full copy of all of the data on tape, and then replicate a 2nd copy distributed around the world. Additional resources potentially available coming from commercial clouds and institutional clusters in HPC. We don't have an exact model for that yet, but we are exploring it actively right now to understand how we incorporate it and how it's going to affect the resource utilization that we have and what we need. So we have been implementing this computing model with data from ProtoDune single phase. There was a beam run in October and November of 2018. We had several different beam samples from 300,000 pi momentum events at 1, 2, 3, and a spread of 6 to 7 GeV. You can see those distributions over here on the right based upon time of flight information coming from the layout here, shown at the bottom at the CERN Neutrino platform. We had 8 million total events from the beam run, which came out to about 600 terabytes of raw data, but we took an additional 50 million cosmic events, and that gave us, that came out to a data volume of 2 petabytes. We have varying purity, high voltage, and xenon doping so that we can understand the performance of the detector and how that those changing conditions affect our reconstruction and our running. But what I want to emphasize is that we have, more than 2.5 petabytes of raw data, and so we feel that that's enough to exercise our computing model. If you want to understand more about how the data management is done, see Steve Timm's talk, which is next. Our reconstruction and processing is based on the ART framework, large soft physics software, utilizing ProtoDune specific modules, incorporating things from WireCell and Pandora libraries. We've been processing 100 event 8 gigabyte files. It takes about 500 seconds per event. We're utilizing 2 gigabytes of memory for our signal processing, about 4 gigabytes for our pattern recognition. And in the end, what ends up being produced from that is a 20 megabyte per event coming out of a 75 megabyte per event raw data. As well, with the 25 hertz trigger rate, it really is equivalent to the DUNE FAR detector beam trigger stream. And the nice thing is that we have processed all of this successfully, and results from all of this processing have now been uploaded to the archive and submitted for publication. And you can see that from the link here. What was our actual utilization when we were doing this processing? So we currently have 36 sites from around the world incorporated within our processing. And we have 13 storage elements as well that are contributing to our storage needs. On the right, you can see that this is the distribution of hours of processing that we have. The inner circle is country. So the US, UK, Czechoslovakia, Netherlands, Spain, Switzerland, France, Russia, and Brazil are all contributing. Right now, it's a 50-50 split. And we want to improve that again to 25%, 75%, but we feel that we're on the way there. Right now, we're just dominated by the fact that Fermilab is providing so many resources that there isn't enough outward bound pressure. At the same time, we've also been utilizing the NERSC supercomputing allocation for running our simulations. If we add that in, NERSC ends up being this large outside band right out here, and it actually ends up being 40% of our total DUNE CPU hours for processing this February through May. We anticipate that we're going to need between 80 and 100 million CPU hours during the ProtoDUNE Run 2 operations. So that gives you a scale for how much we're going to need. As far as tape and disk storage projections going out to 2022, I've given you a little bit of description, 2 archival copies of the raw, derived, and simulated data. What does that come out to? It's going to end up being about 37 petabytes of data for the total DUNE storage, and about approximately 23 petabytes of disk storage so that we can serve all of that data for rapid processing. So computing infrastructure work, we've been working to incorporate additional tools for tracking, accounting, and real-time monitoring. And I have to say that we have drawn heavily upon both Open Science Grid, the WLCG tools to kind of bring the whole thing together. And we've been working extensively with both groups to evaluate, adapt, and incorporating those tools. Recently, we have been doing incorporation of CRIC and WLCG ETF testing framework. As well, we think that it's very important for us to monitor our networking, so we've been incorporating perf sonar as well. So future prospects, so we continue to expand the global nature of DUNE computing, new sites, new contribution agreements, and support models. Our event data model is going to be really challenging to get from 6 gigabytes per event down to an analysis format. Machine learning techniques are really interesting aspect to this because they want to see full images. They want to be very close to the raw data so that they can develop, do algorithms and do training on that, but we don't necessarily want to be distributing 6 gigabytes of data all around the world. There are some new results in inference as a service using some cloud GPU that suggest real great potential there. And we're going to continue to collaborate with OSG, HSF, and WLCG to integrate and develop new features. And that's all I've got. Thanks.
Okay. Thanks, Mike. Great overview talk. Can you, everyone, let me know if you have any questions or if any of the hosts just speak up.
May I have a question? Is it okay?
Go ahead.
Do you hear me? Okay.
Yes.
I, in advance, apologize for the question. We are running time after time some DUNE jobs at our T2 center, and usually they have very low efficiency. Do you know why that is?
This is low CPU efficiency.
Yes.
There were issues that we were having with transfer protocols streaming data into the sites within.
We are on
the Czech Republic, yeah,
WCG.
and it was and I believe one of the problems was IPv6 versus IPv4, and so that is an issue that we're actively working on to make sure that we can improve that.
Okay.
So
okay.
yes,
that explains
we
a lot.
recognize.
Yeah.
Yeah, we recognize that that's a serious issue, and one of the things that was we want to work on is our own monitoring to make sure that we pick up on those issues faster, as opposed to needing the sites to inform us that there are challenges.
Okay, thank you, thank you.
Sure.
Okay, I have one question. I'm really struck by the challenge of trying to get 30,000 CPUs working on a single event with the lowest amount of latency. that's quite a challenge. But is that based on kind of your current reconstruction capabilities, and that maybe some of these things you talked about for the future would mitigate that somewhat?
Absolutely. So right now, this is just based upon our current performance numbers, and we anticipate that there is going to be a lot of different things that we will be able to utilize in order to make that much faster and to lower that number from 30,000 CPUs to, you know, I don't even want to speculate.
It's okay.
Because there are also there's a lot of discussion, and there's been some very good work about utilizing the DAQ and the capabilities of accelerators that are part of the DAQ cluster to send preliminary information out through a path that is different than the continuous readout stream that's very high resolution. So kind of just small pointing vectors from maybe trigger primitives and sending that out for processing after initial processing from accelerators that are in the DAQ cluster. And then that changes the perspective completely. It's no longer 180 terabytes. It's no longer all 600 APAs. You get to chop things up much more finely.
Yeah, and from the multi-messenger, you just need sort of a vector to where to point the telescopes, in a sense.
That's right. Yep.
Great. Any other questions for Mike? If not, we will thank him again and go on to our next talk. So that would be Steve Timm. And yes, he's going to talk about data management for DUNE and our experience with Rucio. Steve, can you say something? Okay.
Do you hear me now?
We do.
Okay. So yes, I'm Stephen Timm. I'm from Fermilab, and speaking as head of the DUNE data management group. I'm going to cover three things in this talk, namely a description of the DUNE data model, our DUNE experience with Rucio, and our plans for a full Rucio-centric data management system. This is a deeply underground neutrino experiment described by my colleague in the past talk. I seem to be the only person at this whole conference that's saying anything about Rucio. So Rucio is a distributed data management software that was developed originally by the Atlas experiment. Other large scientific collaborations, including CMS, LSST, and DUNE, among others, have picked it up. It's a rule-based declarative system. You tell it where you want the data, and Rucio will get it there. It uses FTS3 for file transport currently, but could also use Globus Online, for instance. The DUNE data management currently looks like many other WLCG experiments. We have two proto-DUNE detectors that are both running in CERN right now, each of 5% of the full detector size. We've accumulated 10 petabytes of data on tape so far. About half of that is raw data from the proto-DUNEs, about half of that is reconstruction output products, and a fairly small amount of simulation relative to the rest of it up till now. The event size for proto-DUNE is about 60 megabytes. That's something can easily be transported in one job. We have 36 compute sites around the world, 13 disk only sites, and 4 disk plus tape sites. Proto-DUNE data is archived at CERN and Fermilab, and the other parts are only storing reconstruction output. We stream data via XRD from the closest location that it exists, so in many ways we're very similar to other experiments that use the grid. But we have a few unique things here, and I want to show the challenges that we meet with DUNE. So this represents a typical event from proto-DUNE single phase. So you have 6 APAs going horizontally. You have 3 trigger records going down vertically. So time is on the vertical axis and sub-detectors on the horizontal axis. The 60 megabytes compressed easily can be transported to whatever. Every single thing is what's called trigger record. We don't call them events, we call them trigger records. The smallest atomic unit of data is a data unit. So that's one subdetector for one trigger record. And this whole thing would be called a data object, which is a collection of data units. And I purposely don't call it a file because it may not be stored in a file. By the time we get there, it could be some cloud objects data store, it could be some memory-based store, it could be any number of things. We're still investigating that. Full DUNE, by contrast, has in just one module of the 4, we'll have 150 subdetectors, and as Kirby said in the previous talk, 6 gigabytes per readout. Now, that's a event. If I tried to read all that into memory, I couldn't fit it in memory on most nodes on the grid currently, or as foreseen. So it's envisioned that the detector will actually be split into a bunch of data objects, perhaps one per subdetector, so that this readout may be split into 150 different files by the time we're done. Of course, we will zero suppress this vigorously. We don't expect the whole detector will light up on every single event. So there's not much to gain by suppression, but we have a real problem in trying to stitch things back together once we have done the first part of the processing. At least for the single phase detector, each subdetector is independent, and you can actually process them independently and then put them together later. That's what we intend to do. And that is in fact a very good thing for GPUs to do. So the subdetector from the same trigger record may end up in multiple files. Time slices from the same trigger record may end up in multiple files, especially in the case of the supernova burst readout, where one trigger record will take 100 seconds and all 150 APAs, and we'll have to split by both and get it out fast. Then remember where it was afterwards. In addition to that, we're exploring the HDF5 format for DUNE to store the data. We're exploring non-file-based object storage in general. As previously said, DUNE file detector output is scheduled to be 30 petabytes per year. That is an administrative limit. They could write more if they wanted to, plus more from the near detector. And then we have also the challenge that JSON web tokens, otherwise known as SCI tokens or WLCG tokens, are coming very soon, and we have to be ready for that. So particularly because of the one trigger record split across multiple files, our existing data handling format, our existing metadata format, we conclude is not sufficient for the way Fermilab has been doing things for the last 20 years or so. And we need to write a new system. So we became aware of Rucio in 2018. Somebody says, why don't you run Rucio? And said, okay, we'll try it. And we liked it, and we've stuck with it, basically. The Fermilab Scientific Data Storage Department, it actually operates the Rucio server on DUNE's behalf. It's deployed as a containerized application, and is soon to change to a deployment of Fermilab's OKD, Open Kubernetes Cluster. There's a shared configuration which is maintained by the developers to configure the various containers. Rucio consists of multiple individual daemons. We're using a Postgres database on the backend, which is different than many other experiments use Oracle, and manage all schema and software upgrades. The DUNE data management team under my leadership is using the Rucio clients to move data from point A to point B, asking for help if things get stuck. We are creating and declaring all the new Rucio replicas. We're onboarding new remote storage elements, and we're interacting with remote sites to set up all the transfers. Our current Rucio status is that we still ingest our proto-DUNE raw data from the legacy system and get it from CERN to Castor and tape it Fermilab, and we declare it to Rucio once it gets to Fermilab. We declare one Rucio data set per run, and then we have large containers of related data sets, and then different detector types such as the proto-DUNE single phase, the proto-DUNE dual phase, the eventual DUNE fire detector, the near detector are all different scopes. And we use Rucio to send it to all of the disk locations. We also are using Rucio to manage our limited disk space in certain EOS. So we've taken 5 petabytes of data over the course of time. We only have less than 1 petabyte available in EOS. So we have to rotate off data, and that's worked very well for that. We use our legacy system to tell it what it is and to tell the analyzers where it is, but not for much longer. And we have 17 commissioned Rucio storage elements. We have 13 petabytes total under Rucio management. 1.3 million individual files, 3 million replicas. So when we say 13 petabytes, that's not all unique. Some of that there's 1 or 2 other replicas in the world. This is some of the monitoring that we've done. Our colleagues at Edinburgh have put this together. This is one of our busiest days, and it shows a history of transfers, those that were queued, those that were failed, that were submitted, and so forth. We had a fairly high failure rate because there was one RSC that was down during this time. We also have some management level monitoring that can tell us in the lower right-hand corner, you can see how our replicas are split between various storage elements. The big piece of the pie is Fermilab. The next biggest pie is Castor at CERN. And we will soon be able to show this by country as well, and also by scope. We had an interesting case that we had to get 500 terabytes off of a storage element with 1 month's notice. The storage element was being decommissioned. All of that data was data that existed at least 1 or 2 other places. We had to use our Rucio list data set replicas to figure out what was at that site now, and find 1 other site where it wasn't already, and then make the rules per data set and sit back and wait. And we kicked off on 23 January and finished on 1 February. Then we learned we had 6 months to get out, but we were already out. So the features we know we need going forward, we need a quality of service going forward. In Rucio speak right now, something is either a disk site or a tape site. The public decache at Fermilab, in other words, the part that's not CMS, is both right now. So we need a better way to know when a file's online and on tape, and fetch it from Fermilab when it's already online. Rucio has a notion of deterministic or not deterministic. On deterministic disk sites, files are stored in a hash path. On non-deterministic sites, it's a human readable path that's constructed from metadata fields. So right now we're just putting these in place to write to non-deterministic sites. We need a new feature. And then we're looking for a lightweight client for the Rucio REST API. So the changes that are coming for the future DUNE data management, and when I say future, I'm hoping by the time ProtoDUNE next runs at the end of 21 or the beginning of 2022. So we're currently using Rucio for data movement. We now need to change our data delivery system so that we use the Rucio file location information and use Rucio to deliver it. We have to replace 3 main functions of our legacy system, which does all 3 of these things right now: metadata, replica manager, and data delivery. So Rucio will become our new replica manager. We'll make a new metadata service to determine the file provenance, and a new data delivery system. We also have to replace our data ingest service, which is currently a legacy system. So if you look at the DUNE data management architecture, the data management system is a central box. What we call the workflow system is how other people interface to our system. The metadata catalog tells what it is. Replica manager tells where it is and how to move it between place to place. I have the external metadata box there because the clients will also be able to query things like the conditions database, so that if I want all runs of a certain type that were taken with high voltage of such and such a point, I'll be able to make such a query and get that kind of data set to run on. The data ingest replacement is still in planning phase, but we'll replace our legacy system with a new process that scans the newly created files on the DAQ buffer disks. And they will be files for purposes of going across the network from point to point. That will happen at ProtoDUNE, at the new fire detectors, at the near detector. We will declare the file location to Rucio and the metadata to the new metadata service. And then we'll use FTS3 to do the third-party transfer to Fermilab and from Fermilab to elsewhere, all under Rucio control. This is a schema diagram of the new metadata service. The metadata data sets are very similar to the Rucio model. We have the concept of data sets and files, and then data sets can be parents of data sets and so forth. We also have follow the Rucio notion of namespaces. so that you can have production namespaces, you can have individual user namespaces, and then we have roles of who can create the metadata, who can use the metadata, who can read the metadata, and so forth. And also the concept of arbitrary attributes, some which can be of restricted values of a list, or some that can take on arbitrary values. So the requirements of the new metadata server are complete. We have a reference implementation of that server in testing now. There are already other experiments at Fermilab that are looking to use this metadata design as well. Data delivery and workflow management, we don't like either of these names for it. We're trying to call it something different. In Fermilab, we've been used to defining a dynamic data set and then being able to run over it multiple times. And as new files come in that are added to the data set, that you just get them automatically. And every Fermilab experiment from CDF and D0 onto the present day has had a notion of a project where each job says, give me the next file in the project. And each job notifies the project manager when it's passed successfully, and recovery jobs can be data set. The Rucio, unlike our legacy system, has got fixed data sets. So some important ones will declare immutable, and others will declare monotonic, which you can add but not delete. But you have to you have to run a process to add the files. It doesn't automatically just say, make a data set of all files of this description. So when we talk about workflow management, this is very low level. It's much simpler than a direct or OWM agent. In this case, DUNE will eventually choose a higher level workflow manager, which will interface to this project tracking system. In conclusion, the Rucio is working very well for DUNE to date. There are no known issues that are keeping us from scaling Rucio up to full DUNE. Our goal is to have this Rucio-centric data management system, which I've described by the next round of proto-DUNE in early 2022. And our thanks to the Rucio core developers, to site admins all over the world who work with us, and to the DUNE data management team.
Great, thank you for this talk, Steve. I would ask for questions at this point. Do we have any questions from the audience?
Can I jump in?
Sure, go ahead.
Hi, Steve. Thanks for the talk. I was just wondering how you found working with Rucio as a collaboration for the development of scientific data management. I mean, do you view DUNE as being a customer or a collaborator with Rucio?
So we've had people under DUNE's funding who have actually contributed back to the main stack of Rucio, and the core developers have actually been very cooperative with that. In particular, we had somebody do a lot of work on the site customization part and make that a lot more modular than it was before, and they've accepted that into the Rucio thing. That's in the main release now, so they've been very cooperative in giving us, in taking our patches up till now, and also working on other release features for us that we want without us doing the work also, I would say. And also, for that matter, they've been giving us very helpful advice. For instance, there is a rudimentary metadata server inside of Rucio, but it was the advice of the developers, don't use it for our thing, that we'd better to make our own, because we needed more features than what that could give, and it had never been tested in bulk. I think that some of this monitoring that we've been doing will eventually feed back into main Rucio as well.
Yeah, I
So,
guess I would
we've been
add,
quite happy.
Yeah, I guess I would add that it's a strategic thing for Fermilab as a whole.
Right.
And it really helps that both CMS and DUNE, our two major experiments in the next decade, are committed to it. And that the CERN team has just been great as a collaborator.
Right. And it's the same group that's tasked at working both of these at once. So while their data storage group is serving DUNE, they're also serving CMS, who are also doing this transition at the same time.
Right. So very successful.
Yeah, I think that's a really great example of the kind of collaborations that we need to build for this kind of software. Great.
And DUNE has a decision going forward, which Liz has already hinted to us, that we should make. Should we do as CMS and Atlas and the other big WLCG experiments have done and make our disk and tape totally separate storage elements. And we've been given some nudges and pushes that we should do that, but it has not yet happened.
Yeah. I guess I would say that this is something that has lots of potential even in the R&D sphere. You know, most of what we've been talking about is adoption and deployment. But you know, in the world of global networks and having to transfer so many orders of magnitude more data around the world, we're really going to need network integration that takes advantage of the latest R&D in networks. You know, so at the Rucio workshop, we heard about ESNet 6 and the follow-ons to that I think, you know, it's really of benefit that everybody is using the same system and can benefit at the same time.
And we in DUNE are at the moment, as we speak, working with ESNet to define our networking requirements going forward for the next N number of years. We're doing our network case studies at the moment. Rucio does have some visibility into network latency, et cetera, and it can be tuned appropriately.
Yep. Okay. Anybody else want to comment or question? Okay, if not, then thank you, Steve. We'll go on to the next talk. Yes, we're going to hear about a very ambitious topic, growth and evolution from Run 1, so more than 10 years ago, to the HL-LHC, and we're going to hear from Sharad. So take it away.
Thank you, Liz. So hi all, I am Sharad Agarwal. On behalf of CMS Collaboration, I will be presenting the growth and evolution of CMS offline computing from Run 1 to HL-LHC. The agenda of the whole talk will be introduction to CMS offline computing and the growth and evolution in the three main sectors, which is distributed grid computing infrastructure, data management, and data production. So a little bit about CMS offline computing. So the data that comes into CMS offline computing is through two ways. It's the real data, which is coming from the experiment and the Monte Carlo simulations. All this data goes to the data centers, and then we do different data reconstructions over the WLCG, and the data is sent across different sites through the WLCG, and the final output data sets are produced. These output data sets, which are produced from production, are used by different analyzers to give the final analysis results. So the CMS offline computing uses typical 200K cores of Monte Carlo simulations and data reconstruction. And we help approximately more than thousands of CMS users to analyze the CMS data through the WLCG. So this whole graph is just to tell you when the Run 1 started, when the LS1 is, because we will be talking in the whole talk in these terms of Run 1, LS1, which is a long shutdown one, Run 2, and as you can see, I have circled out that right now we are in the LS2, which is long shutdown 2. So talking about the growth and evolution of distributed grid computing infrastructure, during Run 1, we used middlewares like Glite, htcondor_G, and the Gliding WMS softwares for scheduling jobs over the WLCG. And we started with the grid mesh topology. During LS1, the grid mesh topology was completed, and we also introduced the X2T endpoints for AAA. We also came up with the multi-core pilots introduction during LS1. During Run 2, we completely shifted the whole dependency of grid computing to HD Condor and Gliding WMS. We also switched to Singularity, which is basically removing all the operating systems dependency at sites. And we started doing advanced X2T endpoint monitoring. During LS2, we have been doing a lot of things, out of which one of the major things is the SiteDB to Crake migration. So we wanted to shift to Crake in order to in order to use a software which is coming through the collaboration, the WLCG community. And we started to do advanced monitoring of almost everything in grid computing through Monad Grafana. We introduced partitionable slots in the global pool and started using HPC resources. We have different plans for Run 3 and HL-LHC, which include improving the usage of HPC resources, heterogeneous computing using hardware accelerators, migration of certificates to tokens for authentications, and to complete the migration of the creamed computing element to HD Condor computing element. So this is a very high level overview of the CMS submission infrastructure, where we have the production SCADs and the analysis SCADs, and they connect to the global pool and the CERN pool, and that's how they try to acquire resources. So we talked about the grid mesh topology, which was introduced in LS1. So before that, in Run 1, we had this hierarchical model of CMS grid sites, where the original design was like in tier 0, we had the data where it comes from and the first data reconstruction. The tier 1s were the national centers, which were used only for simulations and data reconstruction. And tier 2s were the regional centers, which were used only for analysis. But CMS wanted to be a little more flexible, and we were able to achieve better overall throughput and better resources with the new mesh topology. So the mesh topology is basically where all the tier 1s, tier 2s can communicate with each other and different tiers. So it gives overall more flexibility and a better throughput of the whole system. So this is the graph which was made through the actual data used from Run 1 till LS2, and it shows how the continuous increase of CPU utilization has been happening from 2010 to 2019, which is the LS2 right now going on. And these are the estimates of the CPU which are required for Run 3 and HL-LHC. So the dotted line that you can see is actually the resource estimates, which are the common resource estimates with the 200 PU. For more insights about workload scheduling and provisioning of CM software and computing, a colleague of mine will be giving a talk on 31st of July. So you can tune in for that. The second main important factor of the growth and evolution is data management. So during Run 1, we had our own software called FedEx, which was developed by CMS, and we used to use it for managing the data. There were different group and site managers which had to do a lot of manual work during Run 1. During LS1, we came up with dynamic data management and the Extrude 3 for AAA. So I will be telling you a little bit more about Extrude 3 for AAA in the next few slides. Then we also had a major upgrade in FedEx, which was using FTS3. And we separated the disk and tape endpoints for tier 1s. During Run 2, we had a complete dynamic data management software, which was called Dynamo. We had advanced Extrude D monitoring, and we also had the Extrude D write support implemented during Run 2. During LS2, which is right now, we have been migrating from FedEx to Rucio. So Steve already talked in the last talk about Rucio. And we have been doing transferring of data via Extrude D. Then we have all these things being monitored on the Monad Grafana infrastructure. And we started working on operational intelligence. The plans for Run 3 and HL-LHC are basically to improve the data management with more intelligent algorithms for efficient utilization of disks and tapes. The second is to migrate from certificates to tokens for authentication. And CMS is also working to achieve the same functionality of dynamic data management through Rucio. So what this Extrude D and AAA we have been talking about is basically the remote data access. So AAA stands for any data, anytime, anywhere. It's an efficient remote data access and important for the flexibility and increasing throughput. All the CMS applications input-output extended to include remote reads. The present technology choice was Extrude D-based storage federation, and the site published the storage inventory to regional redirectors. The central production uses AAA routinely to read input files for data in Monte Carlo workflows, and the physics analysis, data detector commissioning, and other users also save time because no one needs to wait for the data to be transferred locally before they start running their jobs. So you can see the graph on the right-hand side, which shows that the successful remote read has been better than the successful local read. And we had a very low failed remote read. So that's a great thing which was implemented during LS1. The dynamic data management, so the Dynamo software that we use right now for dynamic data management manages about 118 petabytes of disk space, and it uses all the tier, like it manages the space on tier 0, tier 1, and tier 2 sites. So DDM works on 3 main policies. The first one is data popularity. So it basically creates more replicas for popular data sets and lower replications for less popular data sets. The second is the disk usage level. So we try to keep a safe level and use the available disk space. And the third one is a set of policies, which is like, for example, keeping 2 copies of a particular data at different sites, 3 copies of a particular data at other sites, and so on. So these are the estimates for run 3 and HL-LHC for the total disk and tape, which would be required. And here also you can see that the dotted line has been continuously increasing, and we are going to reach exabytes of data on disk during HL-LHC. The third and the last point for the growth and evolution of data product of CMS offline computing is data production. So during round 1, there were a lot of manual work involved, where a lot of people used to do manual submission of workflows using prod agents. So this prod agent is basically the prod skeptics, which we talked about in slide 6. Then the data reconstruction started during run 1, because of course the data started coming in run 1. During LS1, we migrated from prod agents to WM agents, which was a major upgrade. And we started having the remote data access, which allowed decoupling of workflows. So the remote data access, which we just talked about. And during run 2, we had a recovery system implemented in the WM agents, which helped a lot because we don't have to start running the jobs from scratch. If a few of the jobs were failed, we just used to run the failed jobs again. Then a lot of manual submissions, which used to happen during run 1, was all removed during run 2 with the help of Unified, where we used to automatic assignment and management of workflows. Then we introduced step chain workflows during run 2, and we started moving towards open source technologies like MariaDB. During LS2, we have been working on the automation for resubmissions and log analysis, integration to Rucio, and monitoring all the workflow management through Monad Grafana and introducing Kubernetes. The plans for run 3 and HL-LHC is to further improve scalability, shift to more community-based solutions for web frameworks and databases, increasing code currency, horizontal scaling of Kubernetes, and the better usage of data availability. So the decoupling of workflows, which we had with the help of remote data access during LS1, earlier, these particular types of data used to run only a particular site, but with the remote data access being available during LS1, we were able to run different data tiers at different sites. And so you can see that the dotted line shows how we were able to integrate this connectivity in LS1. As of LS2, CMS has more flexibility and everything can run everywhere except the analysis workflows at HLT. So this was a big gain in flexibility during run 2. And all of these data tiers were handled by DDM. For more insights on Kubernetes, how we have been implementing in CMS, we have a talk from one of my colleagues tomorrow in the morning, talking about Monad Grafana, which we have been implementing in almost every part of different structures of the CMS offline computing. So this is just a screenshot of the overall view where you can see we have been monitoring analysis, production jobs, tier 0 jobs, and the submission infrastructure, and almost everything which we can try to monitor through Monad Grafana. The challenges for the future are moving towards heterogeneous computing, supporting continuous development and operations, computing and the storage resources to meet the needs of the future, and developing more intelligent systems for operations. So this brings me to the end of the slide. Although this is just the beginning, and we will continue to evolve and provide physics better than ever. Thank you.
So thank you. This was a very nice summary. I will call for questions now. Does the audience have any questions here? No, I guess it was there. Oh, we do have.
Easy ask, Concetio. Just raise my hand.
Go ahead.
All right. So thanks for this talk, Sharad. You mentioned in several places Kubernetes, and then you pointed also to a talk that will exploit how you use this for CMS web. Is there any other use cases that you are currently exploring? I mean, what are your plans? Is this the only one that you are
in CMS web, we have a lot of different things. It's like all the different services which we use in CMS, and that is the whole thing called CMS web. And we are trying to implement Kubernetes on all of these. So my colleague Imran would be able to give you a better insight knowledge of what they have been up to, because I don't want to kind of destroy his presentation, which is tomorrow.
Okay, thanks.
Okay, Steve, do you want to ask your question?
I was going to ask a related question, namely, have they come up with any difficulties in using so much Kubernetes at this point? Or were there any adoption hurdles that they'd hit? But I guess I should see the next talk tomorrow, and they'll tell us that.
Yeah, I think that tomorrow is also at a pretty inconvenient time for the US time zones. So you might have to see it on the replay session. But yeah, I think that'll be interesting. I happen to know that, you know, the other uses of Kubernetes, you know, would be in provisioning on the sites. And so far, CMS has had a little bit of a hands-off on that, where, you know, there are R&D projects for that, like at Lincoln, Nebraska, they're using Kubernetes together with HT Condor to schedule analysis facility type of notebook jobs. We had a presentation about that at PyHep, which is also recorded if you're interested. But yeah, it's oh, I see that Danilo, who's really in charge, wants to ask.
Yes, I think, yes, Liz, you're right. For what concerns, well, the usage, I fully support the invitation of Sharad to the talk of tomorrow by Imran. Clearly, Kubernetes will become, and we're working hard to make it happen as soon as possible, the backend for the internal services of the experiment. Clearly is a technology which is on the rise. I mean, at ICHEP, there was an entire track dedicated to this and full of talks and nice contributions. Clearly, if a site decides to provision resources through Kubernetes, I think it will be most transparent for the experiments. And I mean, for example, CERN presented at ICHEP a measurement that they did in order to remove some of the overhead, which is very little from the VMs, but provisioning batch nodes through Kubernetes and gaining something which was about 5%. I mean, if you go and look at the slides. So it's something that can be used transparently once it's provided by sites. And internally in CMS is really the portfolio of internal services of the experiment, moving back and taking advantage of the elasticity of this new technology.
Yes, very good, thank you. I don't see any other questions. If that's the case, then we are ending exactly on time here. So I want to thank everybody, and especially our last speaker. I guess we'll call this an end to this session of ICHEP Computing Track. Thank you.
Thank you. Thanks, Liz.
Thanks.
Thank you.
Thanks.
Bye-bye.
Bye.